Introduce the subject and the various methods to deposit the dielectric layer, followed by results, applications, conclusions, and references. I'm going first to start with the basic structure of an organic thin transistor, which is composed of a source and a drain electrode, which can be evaporated on top of an organic semiconductor to give a top contact geometry. Or they can be evaporated onto a dielectric layer, and then the organic semiconductor is deposited above them to give a bottom contact geometry. In general, organic thin film transistors are voltage controlled. They are on-off devices that work once voltage is applied at the gate electrode. Once voltage is applied at the gate electrode. There are two kinds of organic thin film transistors, the N and the P. In the N type, the major charge carriers are the electrons. Once they move, a channel is created between the insulator and the organic semiconductor so that current can flow between these two conductors. In the P-type thin film transistor, the charge carriers are both. Now, the performance of an organic thin film transistor basically depends on the deposition of the active layers, which are the organic semiconductor, the dielectric layer, and the electrodes. My presentation today is about the performance of dielectric layers. The performance of dielectric layers depends on it being chemically and electrically compatible with the organic semiconductor layer. It also must have tunable dielectric properties and low leakage. We achieve this by depositing a dielectric layer that is pinhole free. Therefore, in general, the dielectric layer must be smooth and pinhole free in order for the organic semiconductor layer to perform continuous bridging between these two electrodes. Now, the methods of depositing this dielectric layer are spin coating, inkjet printing, screen printing, and surface-initiated polymerization. I'm going to start with spin coating, which is a method to apply uniform thin films to flat substrates using excess amounts of a solution which are placed on the substrate and then rotated at high speed in order to spread the fluid by centrifugal force. In the paper, they fabricate a dielectric layer using a sol gel process composed of methyl triethoxysilane and tetraethyl orthosilicate. They diluted these compounds with ethyl lactate and deposited by spin coating on a silicone base. It was heat treated in air at 119 degrees Celsius in order to get rid of the solvent. Now, this is a very effective method to deposit the dielectric layer. However, once the dielectric layer is formed, it is usually thin at the edges of the electrode, leading to a lower breakdown voltage. The second method they talk about is the inkjet printing, which is used for printing text and pictures with high resolution. To use this technique to produce the dielectric films, we must replace the conventional inks with specially formulated polymer solutions. Again, the method used to produce this dielectric film is the same as that for the spin-coated dielectric layer, using a sol gel process and treated in air at 190 degrees Celsius in order to evaporate the solvent. Figure B shows an atomic force microscopy image of the inkjet printed dielectric layer. The advantages of this dielectric layer is usually its high resolution and lower cost and the ability to deposit the dielectric layer in a single step. However, its disadvantages is the difficulty to find a suitable ink in order to produce the dielectric layer, number one. Number two, the difficulty to control the spatial fluctuations of the solutes when producing the dielectric film. Because, and the coffering effect is caused when a non-uniform dielectric film is deposited in a non-uniform dielectric film is deposited. This is a disadvantage. It can be prevented, but it is difficult. But it can be prevented by the control of the flow of the solvent molecules, specifically the convective flow and the Marangoni flow. This graph shows current versus voltage for both the inkjet in figure A and for the spin coated in figure B. what's important about this graph is that the slope of the graph is equal to the channel length times the channel width divided by the capacitance multiplied by the field effect mobility. The field effect mobility is very important because it relates to the electrical performance of the dielectric layer. Now for the inkjet printing dielectric layer, the field effect mobility was found out to be 2 times 10 to the power of 3 centimeters squared per voltage per second. And for the spin coated, it was found to be 5 times 10 to the power of -3 centimeters squared per volt per second. The third method they talk about is screen printing, which is a technique that creates a sharp-edged image using a stencil. In this figure, the polyimide layer is the dielectric layer, which is printed through a screen mask on top of a gate electrode, as you can see. Again, the advantages of this method is usually its low cost, its high performance, and the ability to deposit the dielectric layer in a single step. However, it has a limited feature size that can print. The minimum feature size it can print is usually 70 micrometers. However, in ink print dielectric layers, the minimum feature size is 25 micrometers. Again, this is a current voltage diagram. From the slope, we can calculate the field effect mobility, which was found out to be between 0.01 and 0.03. An interesting way to deposit the dielectric film is usually surface-initiated polymerization, and it's specific by ring opening metathesis polymerization, which usually requires 4 things: a strip gate electrode, a linker, a catalyst, and a monomer solution. In the experiment, they used compound 1 and 2 as catalysts, number 3, 4, and 5 as linker molecules. The reaction proceeds by the linker molecule forming a covalent bond to the strip gate electrode through the sulfur atom, forming a self-assembled monolayer. Then, upon addition of the catalyst solution, a reaction occurs, generating a carbon-carbon double bond and a carbon-metal double bond at the other end. It is this part of the molecule that then reacts with the monomer solution through ring opening metathesis polymerization to produce the polymer layer, which is going to act as a dielectric. Now, there were many variables that affect the thickness and the uniformity of the polymer film. Number 1, the type of the catalyst. They noticed that the catalyst produced by catalyst number 2 were far more active than ones produced by catalyst 1. Secondly, and more important, are polymerization conditions. They noticed that polymerization is conducted at above room temperature and for periods greater than 1 hour resulted in great film decrease in thickness due to secondary metathesis reactions, which are chain reactions occurring on the growing polymer chain and eliminating them. Now, there are 2 ways by which an OTFT can be constructed using surface-initiated polymerization of the dielectric layer. First is the lamination method, and again, a current voltage diagram is shown. From the slope, the field effect mobility was calculated to be between 0.1 and 0.3. The second method, which is the direct deposition, again from the slope, the field effect mobility was calculated to be 0.1. The main advantage of using surface-initiated polymerization compared to the others is that it allows the formation of densely packed polymers over any surface topology. Other advantages include mild reaction conditions, short reaction times, simple solution processing methods, and the control of layer thickness by controlling the polymerization conditions. A summary of the results obtained. On the left, we see the method of deposition, and on the right, the field effect mobility. We can notice that the most effective method is the surface-initiated polymerization using the lamination method, and the least effective is the inkjet printing. Now, OTFTs are usually an interesting area because of their decreased weight, decreased cost, their ease of production, and their increased versatility. Therefore, they find application in many areas, including active meter displays, integrated circuits, electronic papers, sensors, radio frequency identification cards. In conclusion, the performance of organic thin film transistors greatly depends on the dielectric layer and its method of deposition. And the optimal performance was observed using surface-initiated polymerization as a method of depositing the dielectric layer. Thank you.
insist. Okay, I'll start again. The title of your talk is Different Techniques to Process Organic Materials for Use in Electronic Devices.
Yes.
Yet, you only showed us field effect and system. Does
Yeah,
that
because
mean...
I focused on the different ways to deposit the dielectric in a transistor.
Okay, so you're focusing on OFET, on processing materials for OFETs. But my question, does that mean you can't use these different techniques, for instance, in making solar cells or making organic light emitting diodes or making other devices? Yes, you can. My second question would be, why do you leave out sublimation as a technique? Because it is very widely used. Just sublimation, simple sublimation. And then a very recent technique has been reported by a Polish group, which is the zone sublimation technique. And these are very, very important.
I found that these methods are the most important.
In your judgment?
Yes.
Okay, I'm going to hold you accountable for this conclusion. You also started by saying in this paper, does that mean you have based all of this from one paper?
No, actually 4 papers, or 3.
Any questions? Any other questions? Fine. Let's thank Mr. Abraham for the presentation. I'd like to conclude this semester and this course by thanking every one of you for the kind work you put into your presentation. And I think, or I hope, that we not only learn how to give a seminar, how to educate people who don't know about a certain subject, how to search literature, how to read about a certain subject, how to write about a certain subject, and most importantly, to learn about so many fields and about so many subjects in the field of organic electronics. This will be the end of this course, and I wish you best of luck. Thank you.